morning. We begin lecture 28. We'll start with a quick summary of the key points of lecture number 27 and then build up on today's material. The topics that we'll be covering is to complete our understanding of the wide sense stationary uncorrelated scattering model. We'll highlight all the different relationships. The purpose of deriving this model was to be able to work with different types of channels. So the classification or the segregation of channels is an important element. And once you segregate, you must have terminology that associates with that. We will introduce that terminology. Earlier, when we were discussing about the different types of techniques in cellular systems like frequency hopping, we talked about wideband versus narrowband signals and how the channel behaves for that. Now, whatever we have studied must correlate with what we have already studied. So that is a very important element. So I would like to establish that link, that whatever we have talked about earlier as wideband versus narrowband will be used. One of the good things or useful things about this course is that whatever you study is actually what is being used by engineers who are building these products. So standardization is very important, and for you to be able to read certain parts of the documents of standards and understand what the terminology they're using. So we will just mention that since we're talking about channel models, in the standards, 3GPP or the ITU, International Telecommunications Union, when they talk about fading channels, what are they talking about? What terminology do they use? We'll just quickly mention a few of those. All of this gives us a theoretical framework. Now, I must be able to generate this in a computer environment which then models very closely what happens in the real world. So there are different methods that are used for generating fading channels, and we will indicate which of these methods. Those of you who have already been exposed to different aspects of wireless will know that probably the most useful model is the Jakes model, but that comes last because you appreciate it more if you know in the sequence in which these models were developed. So let us begin with a quick summary of the points that we have discussed in the last class. So the channel model that we are working with is a time varying dispersive channel, time varying and dispersive channel. Time variation captured by T, the time dispersion captured by tau, and again the picture on the right hand side is a familiar one. We have used it in two of the earlier lectures just to show that there is a delay dimension, there is a time dimension, how we interpret the time variation, how we interpret correlation, how do we interpret the uncorrelatedness between the different delays. All of that is part of our model. So this is, keep this picture in the back of your mind. Now the characterization of these using the power delay profile, that was something that we had looked at in the last class. We said that we could characterize either a continuous power delay profile or a discrete power delay profile. You'll find that most of the time when we work in practice, we are working with the discrete time power delay profiles. The standards ask us to expect us to be working with discrete time power delay profile. So I'll just highlight that as by way of refreshing. We are interested in three parameters. One is the mean delay, the other one is the RMS delay, and then the maximum excess delay. Excess delay is the time gap between the first arriving multipath and the last arriving multipath. So basically in terms of if there was a third multipath component, this would be the excess delay. Okay. Sometimes there may be a path that is considered coming almost with no delay. In that case, your excess delay will start from your first multipath component. Again, keep in mind that it's the first to the last arriving multipath component that is derived that is defined as tau max. Apart from that, there are two other characterizations which tell us how dispersive the channel is. First one is the mean dispersion or the mean delay, which is obtained just like a probability calculation, summation over n tau n's, the different delays times the power delay, the power of that particular component. Usually power delay profiles are given in dB, but make sure that this is not in dB. These quantities are in the linear scale. You have to appropriately account for them. There is a normalization which takes into account the powers of all the multipath components. Please make sure that you do include the component that contributes to the tau equal to 0 component as well. Okay. So let's just like you compute tau bar, you can also compute tau squared bar, and then sigma tau is obtained using our standard way of obtaining the square root of the variance. Okay. So given that you can characterize a power delay profile, the last thing that we did in the previous lecture was to characterize that you could, starting from the time varying impulse response, you could then obtain a autocorrelation function which has got both delta t and tau variations. If I set delta t to be equal to 0, then I can do a Fourier transform. So basically, let me just highlight that. This one assumes that delta t equal to 0. Then I only have a delay dimension, which if I take the Fourier transform, gave me the spaced time, spaced frequency function, spaced time, spaced frequency correlation function. Okay, so that is just a reminder of the terminology that we have used, correlation function. Okay. Now, on the other side, if I took a Fourier transform with respect to delta t and mapped it, setting tau to be equal to 0, or basically ignoring the tau dimension, then I get the power spectral density, because that becomes the autocorrelation, and then this becomes the power spectral density, PSD. Now, of course, you can do the inverse Fourier transforms as well. So I will draw the arrow in the other direction. That will be the inverse Fourier transform for both of these. And maybe there is a interesting question, is that there are two variables. In one side you took the Fourier transform of one, the other you took the Fourier transform of the other. Now, what if you took the other dimension Fourier transform, the second 2D Fourier transform, and it turns out that yes, you can do that. So basically, in this case, I have taken with respect to tau, then I have to take the Fourier transform with respect to delta t. So you can think of another Fourier transform with respect to delta t. Of course, the inverse Fourier transform should take you back, and so this would be another 2D Fourier transform. I'll just call it S hat. The delta t maps to rho, and delta f is not that variable is not affected by this transform. And likewise, you could do another transformation from here. Instead of, since you have already done the rho dimension, do the tau dimension, and basically you can do a Fourier transform with respect to tau. And so I would say that the left, whatever is in purple, is not as commonly used, because that's not giving us much newer insight. Most of the information is captured what is in green and what is in red. So keep in mind that there is a time varying channel response, taken the autocorrelation function, and then derived two very important elements from which we are able to obtain the following characterization of the channel that we are working with. The characterization consists of the following: a coherence time, which consists of which can be written as 9 by 16 pi fd. So that depends on the Doppler side. Again, as we indicated, that comes from the time variation, which comes from RH of delta t. Now, on the other side, when we had the space-time, space-frequency correlation function, we also were able to relate it to the coherence bandwidth, which is greater than or equal to 1 over 5 sigma tau. And this also ties in very well with our understanding that as sigma tau, as your time dispersion reduces, your coherence bandwidth is going to increase, which was the intuition that we also got from the Say and Vishwanath example. So therefore, all of this hangs together very nicely. So there are a couple of rules of thumb which I believe will be helpful for us, and I'll just indicate those just so that you can remember them when you come across them. So the rule of thumb, question that we ask is, when do you need an equalizer? That is, how do you deal with the time dispersive aspects of a channel? So the rule of thumb, which talks about the dispersion aspect, says that equalizer is needed, equalizer required, if your RMS delay spread is greater than T symbol by 10. Okay? So if you have a channel that looks like this, maximum excess delay or it may be quite large, but the RMS delay spread may still be very small and you may be able to get away without an equalizer. On the other hand, even if the channels are close by, but if you have a strong multipath components, then you may have a sigma tau which will require you to have an equalizer. So again, the equalizer is usually a good check for us to see if the equalizer is required would be the RMS delay spread. The second rule of thumb, which this basically talks about the coherence bandwidth, so which says that when is frequency hopping effective? Frequency hopping is effective if your hop spacing, if the center frequency of the hops, and again what we mean by center frequency of the hop is you may be at some carrier F0, next time instant you are skipping to some other carrier F1, the spacing between F0 and F1. That's what we refer to. If the center frequencies of the hops are separated by a frequency spacing that is greater than coherence bandwidth, are separated, I'm going to write in short form, greater than coherence bandwidth. Okay? And of course, why are we saying anything about the coherence time? Yes, you must be doing channel estimation. Channel estimation is needed whenever you exceed coherence time, when your demodulation, channel estimation and tracking. Okay, when the duration of demod becomes larger than coherence time, because that's when you know that the channel has changed and therefore you must be adapting your channel estimates. This is also true if you have had a fade, of course then you have to have another channel estimate that will help you in the process. Okay, that's a sort of putting all the pieces together. So now let's do a pictorial representation of, so what we saw in the last class was that the power delay profile, this is the power delay profile. Power delay profile, Fourier transform gets us to the spaced time, spaced frequency. Power delay profile. This is the spaced time, spaced frequency function, correlation function. Okay, that's from the last class. From the lecture earlier, correlation function. Okay, from the earlier lecture, we have the following results. I have the time correlation, which is in the form of a Bessel function. So this is RH of delta t comma tau, but actually tau dimension is not focused upon here. If this is 1, height of 1 by root 2 is of importance to us, and that's where the coherence time comes into play, okay, connected to the coherence time. And the Fourier transform of this relationship gave us the Doppler spectrum. Doppler spectrum had a inverted or a U shape with the peaks occurring. So this was S of rho comma tau, and this was R H, uppercase H, delta T, delta F, and you are plotting versus from the limits of these were minus FD and FD. Okay. So the channel that we are talking about has got 4 sort of visualizations. One is the time variation and then the corresponding frequency domain interpretation, the tau variation along the tau dimension is the power delay profile and its frequency representation. From this we derive the coherence time, the coherence bandwidth. So, coherence time from the Bessel function, the coherence bandwidth from the space time, space frequency correlation function, and then that helps us in terms of the complete characterization of the channel. Okay. So, this is a good way of keeping all the pieces in place. Now, I would like to introduce some notation and also help you do a classification of channels. So, let us introduce some notation or terminology. Again, these are probably familiar to you, but it is good for us to keep this picture in our mind when we do the classification. Okay. So, very often we have used the term flat, frequency flat. What does flat mean? It is not changing, it is constant, right? It is flat. It is constant, and the opposite of flat is something that's constant is something that is changing, or varying, which we call as selective. So, flat, selective. Again, it can be in any context. So, the minute you see flat, think of something that is constant. When you see selective, you say, okay, something is changing, I need to figure out what is changing. Okay, using this information, let us write down very quickly the common notations that we will use. R1 of t is z naught s of t minus tau naught plus eta of t. So, characterize this channel for me in time and frequency. Z naught is a constant. So, it is time flat. It is time flat. What about frequency? If there is only one tap, frequency response is also flat. This is frequency flat as well. The channel, I am not classifying the received signal, I am classifying the channel. So, the channel description is what we are looking at, channel description. Such a channel, if you have a single tap that is not changing, you would describe it as time flat and frequency flat. Okay, you would not call it a constant channel, because the usage is consistent with the terminology that we are introducing. Okay. Second, R2 of t is z naught of t s of t minus tau naught plus eta of t. Time selective, frequency flat. Time selective, frequency flat. Frequency flat. Okay. I will just write one more to complete my this thing. So, third one is R3 of t is z naught s of t minus tau naught plus z1 s of t minus tau 1 plus eta of t. This is time flat, nothing is changing as far as time is concerned, time flat, but there is a frequency response because there are two taps. So, therefore, your channel will have a frequency response, it is no longer flat, it is frequency selective. Okay. And the last one is, if these become functions of time, this one becomes a function of time, then it becomes time selective, frequency selective. Time selective, frequency selective. Okay. Now, when you read papers, they will often make the following statement. The assumption is that the channel is doubly selective. They do not say anything else, doubly selective. And the interpretation of that is, there are only two things that can be selected, time and frequency. So, the paper is assuming that the channel is dispersive and the channel is time varying. So, basically it is selective, the doubly, because it refers to time and frequency, and this basically means that you have a time varying dispersive channel, time varying dispersive channel. Okay. So, Again, simple notation, but sometimes when you read, it's like doubly selective, what is this, so I don't want you to have that confusion. You should be able to be very, very clear about what the notations are. And even when you describe the channel, don't place Z0 as constant, Z1, no. Please use the terms time selective, frequency flat, whatever the combination is, so that it gives us a unambiguous description of the channel. Okay, if you are now comfortable with the with that part of the representation, then I would like for us to do the following classification of channels. Okay, this is a very important part of understanding the wireless channel and the different systems that we work with in the context of wireless communications. Classification of channels. Okay, I'm going to classify in two dimensions, and again it will become very clear. One is going to be the time dimension, or which is going to be characterized by the symbol duration. So I have a waveform, I have a symbol, there is a duration of the symbol. Okay. Now on the other side, the signal bandwidth. So it's a frequency characterization, frequency perspective. Of course, the symbol duration and the signal bandwidth are related. If you reduce the symbol duration, bandwidth will increase. So again, keep in mind that these are not unrelated things, but for us, for the purposes of characterization, this is what we would like to have as our in our understanding. Now, what did we call as a slow fade? What is a slow fade? That means many symbols experience the same fading pattern, right? That was what we called as a slow fade. Now, how would you relate the symbol duration to coherence time in the context of a slow fade? Symbol duration much smaller than coherence time. Okay, so the one that's going to divide this axis is going to be coherence time. I'll put coherence time here. If your symbol duration is much less than coherence time, we are going to call it as slow fading. Okay, and the minute you become symbol duration crosses coherence time, that means within the duration of one symbol your channel is changing, then it becomes fast fading. Okay, so in this context, I would like you to think about where cellular systems fall. Keep that picture in your mind. Okay. Now, by the same token, let's look at a narrowband versus wideband characterization. Now, the red line, which is the response of the channel, is your actual response based on the multipath that is present in the channel. Now, if my signal bandwidth was the blue one, that was, we said that this would be a narrowband signal because it would look like the channel is almost constant in the duration of the channel. Okay. Now, but whereas the red signal would see channel variation, and therefore the channel is not constant. So between B1 and B2, B1 is the narrowband, B2 is the wideband, lies the coherence bandwidth, because coherence bandwidth is the region where the frequency response of the channel is correlated. So now if you go back, the characterization on this axis is going to be the coherence bandwidth. Okay, coherence bandwidth. Now if you are much smaller than, if your signal bandwidth is much less than coherence bandwidth, then what you will find is that you are going to be, let me use the correct colors, okay. Let me use blue for the bandwidth. So this is going to tell me that I am frequency flat, because narrowband is going to see a flat channel. Frequency flat. I'll just change this to green, change this to red so that there is no confusion. Okay, so this is slow fading versus fast fading. Okay, slow fading versus fast fading. Frequency flat, the minute my signal crosses coherence bandwidth, it is going to see frequency selective. So it's going to be frequency selective on this side. Frequency selective but it can still be slow fading. It can still be slow because this left side of the quadrant is slow fading. Slow fading means many symbols will see the same channel. Frequency selective means that I will need basically there's need for an equalizer. So this means that there is ISI means equalizer needed. That's our interpretation of it. Okay. So just complete the rest of the description. This is frequency flat, and this quadrant is frequency selective, fast fading. Now, very quickly tell me which quadrant GSM would fall into. GSM would fall into slow fading because several symbols are experiencing the same channel coefficients, and the channel is time dispersive, so it's frequency selective. So most of our cellular systems will fall here. Cellular systems, whether it is GSM or wideband CDMA, they are all in this category, and OFDM also will fall into this category if you need equalization. If you don't need equalization, of course, which means that you have created a large number of carriers, so therefore you have avoided equalization in your OFDM system. So OFDM could either be here or it could be here. That means experiencing slow fading, frequency flat, and therefore the receiver is very simple, and that's one of the reasons why OFDM is very popular, because you can design the system so that you don't need an equalizer. So therefore this becomes the so frequency flat means no equalizer or no ISI, so therefore I don't need to worry about the equalization aspect. Most of our cellular systems are in the northwestern quadrant, where it is frequency selective and slow fading. Okay. Now, are there any systems that will fall into this category? That's very important, right? When you classify, if there's some, what does this mean? In the duration of one symbol, the channel has changed. Okay. So which means that it's a very difficult system for you to track, because tracking across even when the channel is constant for many symbols is a problem. Now within one symbol, if the channel changes, it's going to be very difficult to track. So do we have systems like that? We do have, and it is not used in civilian use. These are primarily military frequency hopped systems. They are called fast frequency hopping. Fast frequency hopping because they don't want the enemy to detect where you are. Within the duration of one symbol, the frequency changes. That means you are hopping so fast that within one symbol the channel will change because you are hopping of the frequency. So again, these are very complex radios which we don't build in civilian life, because they are hard to. Of course, the electronics require very extreme complexity. So again, these are used for very specific purposes. So the right hand side is not as common. The left side is where we are. But it's good for us to sort of be able to classify and say, okay, where are we in this space? What are the challenges that we have to worry about? So because it is slow fading, I am okay with periodic channel estimation and some reasonably low complex channel tracking mechanism. If you are in fast fading, those options are out, because you must have a very, very sophisticated algorithm for doing the channel tracking. Okay. So this is an important element. It is tied to our understanding of narrowband versus wideband. It is also tied to our classification of slow versus fast fading, and the conditions under which you would call a system either frequency flat or frequency selective. Again, hopefully this gives us a picture of the complete landscape of what is there as far as the fading channels are concerned. Any questions? Now, what I would like to do is spend a few minutes on one more insight that I would like you to have, and this is very important for the following reason. When we talked about the time autocorrelation, okay, what did we say? The R of t was Z0 of t multiplied by S of t times eta of t, correct? and we said the frequency domain interpretation is that you have to take the spectrum of Z0, the spectrum of the signal, and you have to convolve them, because this is multiplication in time. This is for the time variation, because the channel is time varying. The effect of the time variation on the signal is that there is a smearing of the spectrum. Very clear? No doubt about that. Okay. Now, if I freeze my time at a particular instant of time, at a given time instant t, I have a channel which is given by h of t comma tau. I can visualize this channel as some coefficients that are the channel response coefficients. Now, this is a function of tau. This is the delay dimension. Now, if you were to ask me, forget about the time variation, but tell me how to classify the system, I would say, okay, I am feeding in S of t. There is a black box which is introducing some multipath components, h of t comma tau. T is fixed, tau is the one that is the variable here. It produces for me another output signal r of t, which has got different delayed versions of these components. Now, this input output relationship, because it is not time varying, can be interpreted as an LTI system and therefore as a convolution. So, the output will be r of t can be interpreted as S of t minus tau h of t comma tau d tau. Okay. So, basically it can be interpreted as a convolution because I am not looking at the time variation. This looks like an LTI system, just like our impulse response, input output correlation, exactly the same thing. This is not the same as time variation, because time variation, when I wanted to characterize, I characterize it as a multiplicative operation. This is a convolution operation. So, therefore, how do I interpret the calculations? So, narrowband signal. Remember, we talked about narrowband. How do I understand narrowband signal? Narrowband signal, I transmit a pulse. I have to convolve with the channel, and because the pulse is very wide, my channel is looks very narrow compared to the pulse. So, this is my channel response. So, this is S of t, the transmitted pulse. This is h of t comma tau. Again, the tau dimension is what we are looking at. The convolution of these two produces for me a pulse that looks slightly distorted because of the convolution with the impulse response, but it did not change much. Okay. Very clear? This is the time domain, convolution in operation. If the channel impulse response is much smaller than the duration of a symbol, it does not affect the symbol much. That is the intuition that we have, and that is what is visualized here. Now, the same thing, can you express it in frequency? So, if this was the frequency response or the S of f, the frequency transform of the signal or the spectrum of the signal, convolution in time becomes multiplication in frequency. A narrow pulse is going to give me a very wide band channel. So, this corresponds to a very wide band channel. So, the resultant is I have to multiply these two. What comes out looks more or less like the input, because the channel did not do much distortion to it. This is what narrow band channels are. Okay? And this is the reason why this picture makes sense, because if my channel bandwidth is small compared to the coherence bandwidth, the channel looks like it is a constant. Another way to visualize it is this figure. Now, what would be the same system for a wideband case? So, we are trying to characterize narrow band versus wideband. In this case, the pulse is going to be narrow, right? Wideband signal, you must have narrow pulses, that is when you get wideband. It is going to get convolved with a channel that looks much wider than the, so channel response has got many coefficients. Okay, but the duration is what I have shown here. Okay, that is the impulse response of the channel. So, the pulse is much narrower than this. So the convolution of these two produces for me a totally distorted pulse, and it's much longer in duration than what I transmitted. This is why equalizer is needed, intersymbol interference. Okay. Now, what is the frequency domain interpretation? This is S of t, this is h of t comma tau, sorry, it's lowercase h of t comma tau, and again the dispersiveness of the channel is visible here. If I were to look at it in terms of the frequency, S of t is a wideband signal. The impulse response of this channel, now I have to multiply the impulse response or the frequency response of this channel. It's got some frequency characteristic. I multiply these two, what comes out is that my input signal is now has got some effect of the, so the product of these two is a channel. I don't want the time domain and frequency domain to look similar to each other. Let me just redraw this. Something, okay. So the product of these two is what is shown here. Okay. So the frequency spectrum has got distorted, which is exactly what you saw in the case of a wideband. If I have a wideband channel, the frequency, when it passes through a dispersive channel, its frequency response will get affected. Okay. So I just wanted you to be clear in terms of our classification, in terms of our visualization, in terms of narrowband versus wideband, time domain, frequency domain, all of those pieces should be together, because only then we can make clear interpretations of the classification of channels. When is it narrowband? When is it wideband? So where is it narrowband here? When you are much less than your coherence bandwidth. So this is the narrowband portion of it. Okay, this is the narrowband portion of it. So here is narrowband and here is wideband. Okay. Now again, depending upon the dispersiveness of the channel, a narrowband signal can become a wideband signal because you can see frequency variation. So again, keep in mind that it is a classification that requires you to understand and have the insight of how you have come about with the classification of the system. Okay. So again, if there are any questions, it's a good time to stop and ask, and we will then move on to the next. Any questions? If you want to just look at your notes, see if you are clear about all the things that we have spoken so far. Now I want you to look at the channel models that are used in standardization. Channel models in standardization. And the best reference for us to read other than the standards themselves is Molish, not in the textbook, but it's a online appendix, appendix 7C and 7D. You can download it. I will give the link on the web, on the Moodle page. 7C and 7D. They give us two of the most commonly used models. Appendix 7C. Again, I just want to indicate a couple of examples so that you will appreciate that whatever we have done actually ties in what we have. Okay, Appendix 7C says that there are 4 basic channel types, and those 4 basic channel types are rural area, using the acronym RA. Then there is something called a typical urban. The difference would be that rural things would be far apart, lower height of buildings, not many reflectors, whereas in a typical urban you would see higher buildings, lot of reflectors. And then there is a third channel characteristic. There is something called bad urban. Has nothing to do with crime, it only has to do with propagation. This is BU, which says that there are lots of very tall buildings, and therefore you can have signals just bouncing off buildings, many buildings. So it's also referred to as a canyon effect, because the signals can propagate because of bouncing, and of course this can cause long delays in your received multipath signal. And then there is a typical urban, and then there is a hilly area, HA. Now, interesting for us to see, I would definitely like for you to go in and see the different channel models and how they are described. These are described by means of the power delay profile. Power delay profiles. Let me take just two examples to give you that. For rural area, the power delay profile is given as RH of tau is equal to e power minus 9.2 tau if tau is greater than 0, less than 0.7 microseconds otherwise. Okay. Now, very important, sketch this. So, the outer limit is 0.7 microseconds, that means no multipath beyond 0.7 microseconds, and it is a exponentially decaying profile, and it decays very fast because the exponent is 9.2 times tau. So, this is 1, and then it decays to, by the time it reaches 0.7, it decays to 1.6 into 10 power minus 3. So, that is the power delay profile. And now, what if you wanted to sample this power delay profile, then what you would do is sample it at different points in time and then implement it based on whatever sample spacing that you want based on your discrete time representation. So, that would be one way of understanding the power delay profile. Okay. Now, the same thing using the experimental characterization, they also have given it in the form of a table. So, by the way, these are referred to as the COST. That is a project which dealt with the characterization of channels. COST 207, it is called COST 207 channel models for GSM and other wireless systems. Now, they have classified it in terms of a power delay profile. You can also see in Molish chapter 3 there is a table 7.3 which has the following. It says you can define it in terms of a discrete time, discrete model, tap number, delay and the power in dB. Okay, that is a third column. There is a fourth column. I will not comment on that until you read it, because only when you read you will ask the right questions. So, they have described the rural area in terms of 4 taps. The first tap they say comes with this is delays in microseconds. Second tap at a delay of 0.2 microseconds, 0.4, 0.6 microseconds are the different delays. The power levels 0 dB, minus 2 dB, minus 10 dB, minus 20 dB. Okay, it does not follow the exponential profile exactly, but there is a reason for that, because that has to do with the spectrum, the fourth column. But you can understand that the description of a channel is very, very close to what we have been talking about, where you say you take the power delay profile, you characterize it, and then each of these has got delay and has got a certain power level associated with that. So, please do read, you will appreciate the aspects that are given there. Now, I would like to sort of tell you what the bad urban looks like. Okay, bad in terms of the propagation. The bad urban, and I have skipped over typical urban, you can look at it, that is a exponentially decaying profile, maybe just does not take much time. Typical urban looks like this. It is a much slower decaying exponential, that is all, because that means there is more multipath that is present. So, it goes all the way up to 7 microseconds, that is typical urban. Now, bad urban on the other hand has the following behavior. It has got a decaying exponential like the typical urban, but at 5 microseconds it does this. What does this mean? Bad urban, that means because of the propagation environment, suddenly at 5 microseconds there is a strong multipath component that is present, multipath component. So, you think that the multipath has almost died down, and you find that no, suddenly there is a multipath component that is springing up from somewhere. Now, hilly, hilly terrain. Did I call it HA? It should be hilly, no, it's hilly terrain, HT. This should be hilly terrain. HT. Okay, hilly terrain, again very intuitive. Let me just sketch it for you. Describe it. No multipath components. Okay, so therefore it dies down very fast, but there may be a hill or something of which the signal reflects, and that can come with a long delay, much longer than you can see in an urban environment. Suddenly, there is a multipath component, not as strong as the original one, but nevertheless at a strong multipath component. So again, these are based on the different types of environments that people observed when they were actually deploying GSM. Some were dense urban, therefore you could see that the multipath was lingering for a long period of time, and then suddenly there was really bad propagation. There was an unexpected multipath components. Again, hilly terrain and rural areas are present. Okay. Now appendix 7D has got additional models, but I would like you to see that as well, because it has something that is very useful for us. It has indoor models. Notice that the previous ones were all outdoor, rural, urban, bad urban, all were outdoor models. Indoor models, what if you are indoor? There are indoor A, indoor B. Then it has got something called a pedestrian model. If you are inside of a building or just outside buildings, there are two models, and then of course it has got vehicular models as well. These pertain to the channel models used by ITU, International Telecommunications Union, which they specify that you have to test your system against these models. And of course there are several variants of these, variants for sectorized antennas, variants for MIMO ... So many variations are there. But once you've got an understanding of what are the basic models, how are they classifying, what are the things that they are doing, then it becomes very easy for us. So for example, when you look at the description, I want you to pay attention to something. The indoor channel model, this is channel indoor A. It has got 6 multipath components, tap number, this is the delay and the power level. Okay, power level. So 1, 2, 3, 4, 5, 6. This is 0, 50, 110, 170, 290 and 310. The power levels 0 dB, minus 3, minus 10, starts to look like an exponential, minus 18, minus 26, minus 32. Okay. Now guess what is the units for the middle column. If your outdoor model was 0.6 milliseconds, microseconds, so this would be definitely less than that. These are nanoseconds. These are nanoseconds. So it is basically much less than a microsecond, much less than what you would see in a outdoor environment. So again, the things for you to keep in mind are what are the types of delays that you are seeing, what are the power levels, what does the profile look like. Again, that would help you appreciate what we are discussing. Okay, I will leave you with one last question. Now at the end of it, we have now fully understood the wireless channel. I know you can tell me whichever way you want, fading, flat, frequency, everything. I know I can characterize it, I understand it. Now I say please implement it, go ahead and implement it, show it, do it on a computer. So the student does the following. This absolutely no problem, I know all the theory behind this. I am going to take one random noise generator, Gaussian, I will take a second Gaussian generator. So this is a white Gaussian. What does white mean? Uncorrelated. So basically I am generating Gaussian noise, uncorrelated Gaussian noise, and in digital communications we know how to do that. So I am going to take 2 of these white Gaussian noise. I am going to multiply this by j, add this together. This I am going to call as ZR of n discrete time. So, this I am going to call as Zi of n. The combination of this is Zr of n plus j times Zi of n. Now, I asked the student, are you sure this is the fading channel? He says, absolutely sure. Real part is Gaussian, imaginary part is Gaussian, complex Gaussian, I add the two together, I have got, and by the way, this has got Rayleigh envelope. Anything missing? Delay is mod. This is for a single tap, frequency flat channel. Only one tap is needed. If I change Zr of n to Zr plus n plus 1 and Zi to Zi plus n plus 1, is there any correlation between these two? No. Why? Because independent samples were being generated. But now, if I am in a fading environment, if you suddenly tell me, from I just moved my time observation by a few milliseconds, and you say the channel completely changed. No, that's not possible, because you know that the autocorrelation function is actually a Bessel function. Until you reach coherence time, the channel has to remain correlated, but this is totally uncorrelated. So the question is, this is okay, because it will generate the right Gaussian the Rayleigh statistics, but it does not capture the time correlation. How do I ensure that the samples are time correlated? That is, my channel at this time instant is like this, next time instant is like this, ... So basically there is a correlation that has to be present. I cannot get this at one instant this time, next one is this, third instant is this. That is not the type of channel that we are encountering. So something is wrong with this figure. Okay, and obviously what is it that we need to fix? Time correlation is not present. So we have to do something to this one. Okay, think about what it is that we do. We'll present it in the next class. Thank you.